We've seen in earlier videos how columns can buckle. This is called flexural buckling because the column buckles by bending. There are many other kinds of buckling. For example, here is a column that has buckled by twisting. So if we look at the top view here, we see that the column has actually twisted in this way. This is called torsional buckling. A column can also buckle by both bending and twisting at the same time. That's called flexural torsional buckling. Shown here are a lot of thin-walled sections, often made by cold-forming sheet metal, cold-formed sections, which are prone to different kinds of buckling like flexural torsional buckling. Not only can columns buckle, but even parts of other members that are in compression can lead to buckling. One example is here is a beam that's being loaded in the middle, and we see that the top flange of this beam will be in compression and the bottom flange in tension. And because the top flange is in compression, it has the tendency to buckle. It can't buckle by deflecting downward because the stiff web is keeping it from buckling downward, but it can buckle outward in this way. And as it does that, it kind of causes the beam to bend in the lateral direction as well as causes the beam to twist. So before buckling, the beam looks like this, and then after buckling, like this. This is called lateral torsional buckling of beams. And we will talk a bit more about this in the next video. But we see that if, for example, there is a deck that is cast on this beam that prevents the top flange from buckling outward, so if the beam is laterally supported on the compression flange, then lateral torsional buckling cannot occur. But if the beam is not fully laterally supported, then it has the potential for lateral torsional buckling. We'll talk a bit more about this in the next video. Yet another form of buckling that can happen is here's the column, and we see that the flange itself is in compression, and then just a little segment of the flange can buckle out like this, and this is called local buckling. Similarly, this top flange of the beam is in compression, so a part of the top flange of the beam can buckle, and that's called local buckling of the beam flange. When a beam cross-section is such that it fully yields before local buckling can happen, such a cross-section is called compact section. Yielding occurs before local buckling. Otherwise, this section is called non-compact. The propensity of a section for local buckling depends on how thick the flange is compared to the width. The ratio of W over T determines the propensity of a column for of a flange for local buckling. The larger the W over T, the more likely there is to be local buckling. So if we look at this table in the AISC manual, we see, for example, the W14 by 99 has a superscript F, which says the shape is not compact. So there are some sections that are not compact. That has to do with local buckling. And finally, there are still other forms of buckling. For example, the web of a beam is in shear, and when a square such as this is in shear, we see that there is compression. There is compressive principal stress in this direction, which can cause buckling of the web. This has to be accounted for in the design, for example, of plate cutters. We won't talk about such things in this course. You will look at these in much more detail in the steel design course. For now, in this course, it's important to understand what lateral torsional buckling is, which we will talk a bit more about in the next video. And it's also important to understand what a compact section and non-compact section is. In the next video, we'll talk about lateral torsional buckling.